test afterwards.
All right, I will begin with a word of prayer. I think it's time. Yeah. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray you'd help us to glorify you this day, Lord. In your name I pray. Amen. So, we are on to chapter 12, which is on residues. So, in some sense, we're not really doing new math. We're really just capitalizing on what we've already done. But our attention is going to turn to just calculating the minus one coefficient in the Laurent series, and that's called the residue. Now, because of the formula we found in connection with the generalized Cauchy integral formula, we know that that has the significance of calculating a certain integral. And we're going to be able to exploit that to calculate a number of integrals that are just really hard to do without this, well, technology, if you will. So, all right, so let me get started here. Welcome to the visitor. All right. Where are we here? Oh, my stupid notes have chapter 11. I was about to start into the Laurent decomposition again. That'd be horrible. Let's get on with it here. So this is section 12.1, which is on the residue theorem. So what I'm going to do is define the residue, and well, we've done that before, but I need to revisit it. And then once we've defined it and learned a couple tricks for calculating residues, then I'll state the residue theorem, hopefully. All right, so here we go. So suppose you have a Laurent expansion on 0 less than or equal to rho less than, modulus of z minus z naught less than sigma, which is less than or equal to infinity. So we've got some sort of annulus, right? It could have 0. It could go out to infinity. It might contain the center. It could be a disk, right? It could be the whole complex plane. I mean, lots of choices depending on what we make rho and sigma here. But we've learned that on any such annulus, be it degenerate or not, we can find a Laurent decomposition, Laurent series expansion for a function which is analytic on such an annulus, right? And so that looks like the sum n equals minus infinity to infinity of a sub n z minus z naught to the n, right? And we also have previously learned that a sub n is equal to 1 over 2 pi I, the integral over z minus z naught, bless you. Is that the right thing to say? I don't know. Anyway, sorry for your cough. It's your, that also seems wrong. I don't know. What do you mean? Seems like bless you should be reserved for sneezing, but what do you? Bless you's for everything? Oh. Okay. So you're just trying to make me to agree with your practice to normalize your weirdness, right? Okay. I'll allow it. Okay, z minus z naught to the n plus 1. So that's and where is this r? So we have in mind, possibly rho is the inner radius. Out here is sigma, the outer radius. And, I mean, those could be, again, rho could be 0, sigma could be infinity, but this circle of radius r, it's somewhere in here somewhere, right? That's the r that's in play. And the interesting thing is that that coefficient can be calculated with any red circle between the inner circle rho and the outside circle sigma. They all give the same integral, and the meaning of that integral is revealed in the coefficient of the Laurent series is that integral. So we make a definition that the residue of f of z at z naught is equal to a to the minus 1. A sub minus 1. All right. And of course, if you just focus our attention on the residue, what's the significance in terms of integration? So notice that the integral of what happens when we put in n equals minus 1 here? We get z minus z naught to the what? 0, right? So that's just the integral of f of z dz over this circle. And that's 2 pi I a minus 1, right? Or in terms of the residue, 2 pi I times the residue of f of z at z naught. So in short, we can calculate this sort of integral by just calculating the minus 1th coefficient of the Laurent series, which isn't too bad, really. So let's just look at some examples of residues before I go on to talk more about the residue theorem. So first of all, residue 1 over z minus z naught is equal to, well, this is really dumb. I'm ashamed I'm even writing this. That's 1. In contrast, the residue of 1 over z minus z naught to the n at z naught is equal to 0 for n greater than or equal to 2. Actually, I could be more greedy than that. I could just say for what? For n not equal to minus 1, right? Well, for n not equal to 1, rather. So in all these cases, it's kind of a silly Laurent series. It's like a Laurent series with just one term, right? That's either a reciprocal term or a Taylor type term, positive power term. But any way you slice it, if n's not equal to 1, that's not a residue, right? Okay. And a more interesting example, we have calculated before that if you take z cubed plus z plus 1 divided by z squared plus 1, what do you get? Partial fractions decomposition gives us z minus 1 over 2i, 1 over z plus I, plus 1 over 2i, 1 over z minus I. So this is the partial fractions decomposition. And from this, you can see some different things about this function, right? It's got singularities, right? It's got a pole at plus or minus I, right? And if we think about what we learned in chapter 11, the residue is going to be 0 at any point which is what? Not a pole, right? Well, is that true? I don't know if that's obvious yet. Any point where it's okay, fair enough, if it's holomorphic, but right. Sorry, I was thinking about something else. Let me stop thinking. Wait a minute, no, that seems wrong. The residue of f of z here at I is what? So if you look at this at I, z is holomorphic, right? 1 over z plus I is holomorphic because when you plug in I, you just go 1 over 2i, right? No problem there. So these are both can be expanded as a Taylor series at that point. So all of the reciprocal terms in the Laurent series expansion come from this, and that is exactly it. So the residue here is just 1 over 2i. And if instead I put minus, what happens? If I put a minus here, I do what? I pick up that minus, right? For the same reasons. All right, so if we already have the partial fractions decomposition, we can read residues by just looking for linear reciprocals, right? But it'd be nice to have, a more robust method. So let's kind of get towards that. Here's another example. One more example that's not based on anything except for just direct calculation. So here's sine of z over z to the 6th, right? And so that would be 1 over z to the 6th times z minus 1/6 z cubed, 1 over 120 z to the 6th, and so forth, right? And so what's that give us? That gives us 1 over z to the 5th minus 1 over 6 z to the what? 3rd, right? And then, oh, I'm an idiot. Yeah, that should be z to the 5th, right? The power series expansion sign. Thank you. So plus 1 over 120 z, because z to the 6th dividing into z to the 5th gives me 1 over z. All right. In fact, that's already the principal part of the Laurent expansion at 0, right? Anyway, the larger point here is what's the residue of the sine of z over z to the 6th at 0? One over 120, right? It's not complicated. You just got to calculate the Laurent series and tilt your head and squint and read it off. It's just that simple. But it has profound implications. Like, here's an application. Where is this the Laurent series for sine z over z to the 6th? We're on 0 less than the modulus of z, right? It's actually for the punctured plane that this is the Laurent series, right? Well, centered at 0. So there are, no, that's the only pole, yeah. But anyway, my larger point here is if we were to say integrate around the unit circle, right? Sine z over z to the 6th, what would we have? We get 2 pi I times the residue of sine z over z to the 6th at 0, because this fits the theorem we wrote down, right? This is the context in which the integral is calculated from the residue. There's just one pole, and we have, if we could draw a picture, here's 0, here's the unit circle, right? And so this is just, 2 pi I over 120, right? Or pi I over 60, if you like. Not bad, right? All right. So let's look at the Cauchy residue theorem. The more exciting one is, suppose D is a bounded domain. In the complex plane, all right, with piecewise smooth boundary. All right. And suppose that F is analytic on D union the boundary of D, except at a finite set of poles Z1, Z2, ... Zm. My notes say finite number of isolated singularities. No. I believe we need poles. Well, is this still true if it's an isolated, if it's an essential singularity?
I assume you would need to say rho is strictly greater than 0 in that case.
Yeah.
So would you probably, you wouldn't always get the same thing. No, wait, no, yeah, that's still the defined.
I think it might still make sense for an essential singularity. I'm going to have to put a question mark on that for the moment. I'm worried about it, but I'm not sure I'm worried with cause. So it's definitely true if they're poles, all right? So in D, all right, then the integral over the boundary of D of f of z dz is equal to 2 pi I times the sum of the residues. So the proof of this follows immediately from the theorem that we already have stated today on the other board. We just need to draw a picture to try to envision what this would look like. So what you do is let's kind of, in our mind's eye, envision a bounded domain, right? Could have holes, right? Not saying it has to be simply connected. It could be something kind of weird, right? I mean, the domain might look something like, might have some holes, right? Whatever. And then there's some singular points, right? I'll draw the singularities in red. The point is, we can chop up the region D into subregions, right? That contain just like one singularity, right? Here we go. I think I need one more cut, right? So if you look at, this is maybe this is Z1, this is Z2, Z3, Z4, Z5 in my picture. Then on any one of these bounded domains, we can calculate the like say if this is D1, well then the integral around the boundary of D1 of f of z dz is equal to 2 pi I times the residue of f of z at z1, right? Why don't any of the other poles matter to that calculation? Because if you think about the Laurent series expansion based at z1, the part which is singular at all those other places, well, it's holomorphic close to z1. It's only the part of the function which is, singular at z1 that contributes to the residue at z1. And this story repeats at hz, right? If I look at the Laurent series expansion of the function at z2 and I apply, what we learned in chapter 11, right, to integrate around this D2 region that I'm pictured with its funny hole, then again, the residue of the function at z2 is going to pick up the integral around the boundary of d2 because the part of the function which is singular at z1, z3, z4, and z5, it's actually holomorphic in this region, right? So the theorem follows because we just have to. Well, the other thing is, of course, what's the deal with these like the boundary of, how does it work when you look at the boundary of like D2 with D3, what happens there? This is the usual story, right? D2, if we, the usual orientation, D2 is going that way on that inner edge, right? D2 goes like that, like this, right? Like that. This is the orientation of D2. What's the orientation of D3 look like? So D3 looks like that, right? So any of the cross cuts inside the region, those cancel out. So when we add together the integral around each boundary going across, all that we're left with is the outer boundary of the actual D. Like over here, we've got like this, but then here, the inner cut is canceling out. So when we sum j equals 1 to m, the integral over the boundary of dj, f of z dz, that just gives us the integral over the boundary of d of f of z dz. But on the other hand, each one of these is 2 pi I times the residue of f of z at zj. Okay, so that's why we have this result. Okay, while I've got this on the board, let me use the residue theorem to calculate an integral. Yeah?
You said in the notes that
Uh-oh.
it's somewhat of a history question, but I'm just kind of interested. There was like a section in the notes where Cauchy said something like Laurent's idea of decomposing functions seems interesting, or something like that, and that was dated like 1840 some. But then there's a different place where it said that people were doing like residue calculations by the end of the 18th century. So is there, like when this theory was originally being developed, was there an idea of residues without?
Oh, 18th, as in like late 1700s.
Yeah.
Oh, I don't know about that. That's interesting. But definitely I think as it applies to complex integration, right? So that letter that I have in the notes from Gauss to Bessel in like 1811, he's describing complex integration wrapping around the pole of 1 over z, developing different logarithms, right? That's before any of these things have been published. He just has an idea about what complex integration must look like. But on the other hand, Euler used complex numbers to calculate things. And Euler was a master of series manipulation as well. So is it possible he uncovered some of these things without ever writing an integral down? It seems entirely plausible to me. I don't know. That's an interesting question. How is it that people were looking? Is it just a typo in my notes? Maybe. Or was there actually a sense in which residues were studied in the late 18th century and yet were only formally developed for complex integration in the mid-19th century? I don't know. That is an interesting question. You should remind me later where it is in my notes that I say the other thing, so I can try to backtrack where I found that comment and try to dig into it. It's interesting. So while we have this and we have that, let's apply it. Can you guys think of a contour? By the way, the boundary of D is usually called a contour. We start talking about contour integration. Can you think of a contour which will encircle both of the singularities of my second or my first interesting example of residues? Where are the singularities? Plus or minus I, right? So you got I minus I. So actually it doesn't matter. Take literally any curve that encircles both of those, right? In the counterclockwise sense. Then the integral of f of z dz is what? It is 0, yes. Because it is 2 pi I times the residue of f of z at I plus the residue of f of z at minus I. And those are 1 over 2i and minus 1 over 2i, or vice versa. I can't remember which is which, but oh, this one was minus 1 over 2i, and this one's 1 over 2i, so the net is 0. On the other hand, if you wanted to get a non-trivial integral, or you wanted to, confuse students, you could do stuff like this. How about C2? What's the integral around C2 of f of z dz? You got to be careful, right? Like one of the loops of this figure 8 is clockwise, one is counterclockwise. The residue theorem is set up for counterclockwise oriented loops, or deformations thereof. So this one's counterclockwise, right? This one's clockwise, isn't it? Or are they both counterclockwise? I managed to make them both counterclockwise. That's no fun. Dang it. I confused myself, yes. Here, let me unconfuse myself. Let me be annoying. There. Now the lower one's clockwise, but the upper one is counterclockwise. That's annoying, isn't it? There you go. Okay. Anyway, I don't want the answer to be 0 again, which is what it would have been if I left it. So now the answer is not 0 because the top one, let's say this is C top and C bottom, ICB. So integral over C top, f of z dz, plus the integral over the bottom, f of z dz. But the thing is, the bottom one, to reverse the orientation, I do minus and a minus here. And then the reversal of CB is counterclockwise oriented. Consequently, I can apply the residue theorem to that. Right? And so then this, the top is 1 over, well, okay, so residue theorem both. We've got 2 pi I times 1 over 2i minus a minus 1 over 2i. So in short, I believe, if I've set this up right, the integral would be, let's see what we got here, 2 pi. So these are games we can play. Yeah. Kind of like that homework problem we had. Remember the one with like the C1 and the C2 and the those are still issues here. Yeah. Now, why would you say it's not a contour, but it is a curve?
Because you said it contours the boundary of a region, right?
Contours the boundary of a region. Ah, fair enough. Is that a region? Ah, yeah, we're on the edge of where I know the answer to your questions. So, is that connected? I mean, I think it's connected because there's this point that we can run.
You have to have it be the boundary of the domain, right? If it's the boundary of a region, it's the boundary of the domain.
Now, definitely the thing is the boundary of, if it's an open thing, is not a domain because it's not connected. You got me there. So you say I should say it's a curve, but not a contour.
Yeah, so you can apply Cauchy's
Yeah.
theorem to the two separate parts, right? Just not the whole thing.
Right. Yes. Okay, so where's I got rules to share with you guys. Because fortunately, we don't always have to just straight calculate the Laurent series decomposition to read off the residue. We can actually focus our attention to calculate residues with a lot more efficiency than I've been doing up to this point. There are 4 rules in particular that often serve us well in the calculation of residues. So the 4 rules. Rule numero uno. It says that if f of z has simple pole at z naught, then the residue of f of z at z naught is equal to the limit as z goes to z naught of z minus z naught times f of z. In other words, we can clear out the pole by taking the limit in this sense. Rule number 2. So I'm going to state all the rules and then we'll start thinking about their proofs, okay? We just go ahead and state all the rules, make sure we get them stated. Rule number 2 is if f of z's got a double pole, at z naught, then to calculate the residue, what do you do? I gotta say, these first 2 rules don't excite me that much because they kind of require a lot of me, you know? In the sense that I need to know I've got a double pole or a simple pole already, yeah? So these are not entirely self-contained. I mean, there's kind of a lot of intellectual capital going into these rules, yeah. Ah, yes. Indeedly doodly. I'm missing my derivative, which is important. No derivative, no correct. All right. And then rule 3. And I believe the numbering, well, I'm not sure who wrote these rules down with this numbering first, but I know that I got this numbering from the classic text by Churchill, which is where I learned complex variables from, and which is also where Dr. Sprano learned complex variables from. You'd have to ask Dr. Skimbourdis. I'm not sure if he had Churchill, but it's been around for a while, this book, Churchill. I don't use it because I think they're better books, but it's still a good book. Rule 3, but I don't want to have students pay $170 or whatever ridiculous price it's 14th or 15th edition it's in. I don't know, it's one of these books that the publisher holds on to and like just keeps new editions, new editions, new editions. Yeah. Well, I mean, in principle, but it's not so easy to do that sort of thing with a bookstore, in my experience. So it's just easier to say no book. All right, if F and G are in, well, excuse me, what does this notation mean? Now we got something. I like this one. It's got no limit. Right. The application of this rule is limitless. So that notation means that F and G are holomorphic at Z naught, right? So if you've got a pair of holomorphic functions at Z naught, and you have a simple 0 in the denominator function, that's the residue. Rule 4, if G of Z has simple pole at Z naught, right, then the residue of 1 over, I guess all of these require some knowledge. I was hoping for some lazier thing. I've been away from this for too long. I've forgotten that these actually require thinking. But not too much. Let's see here. Not too much.
And then in your reply to my email, you said that rule 4 should say 0 instead of whole, right?
Yes. Yeah. Thank you. Let's fix that. This printout is from before. I think I still need to implement your change in my notes. Otherwise, we'll be doomed to repeat these mistakes next offering. Yeah. Okay, so these are the 4 rules. Yep.
Are the third and fourth ones basically the same? Just like
Yeah.
Okay.
Yeah. In some sense, 4 is really just a special case of 3. So if we can prove 3, 4 automatically follows. Let's. Where do you guys want to start, proof-wise? I don't think the proof of any of these are terribly difficult. How about, let's look at rule 1. How would you prove proof of rule 1? What would that look like? So let's assume that f has a simple pole. Then f of z equals to z minus z naught, right? Times h of z, where h of z is holomorphic at z naught, right? And h of z naught is equal to, well, it's not equal to 0 is the point, right? This is what it means to say that f of z has a simple pole. Excuse me. Oh man, pole. I'm missing something, right? Namely, division, right? So this was, actually that was not the definition, but this is a result that we had from chapter 11, right? We proved that if you have a simple pole, you can write the function like that. And so then, thus, the limit as z goes to z naught of z minus z naught times f of z is equal to what? Sorry, I'm getting to the point very, very slowly here. But what is h of z naught? So h of z is analytic at that, so it's got a0 plus a1 times z minus z naught plus da 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 da. So what's that say? That says that f of z is equal to a0 over z minus z naught plus a1, fine, plus a2 times z minus z naught and so forth, right? Therefore, the residue of f of z by direct computation is a sub 0, right? But what is a sub 0? What happens if we plug in z naught into h of z? What's h of z naught? It's a0, right? So this is equal to h of z naught, and that proves the rule 1. I think the proof of rule 2 is pretty similar to that. I'm going to look at proof of rule 3 because I think that one's more interesting. Okay. So let's see here. Rule 3. what do we got to work with? We have G is a simple 0. Let's see here. So we have f of z is equal to, let's say, a0 plus a1 times z minus z naught plus, a2 z minus z naught squared plus dot dot dot, since what? Since f of z is holomorphic at z naught. Also, g of z is a simple 0, right? So g of z is equal to, what is it? It's equal to b see, I thought by writing the series out I would make my life easier this time. I may be wrong. So g of z is a simple 0. Good grief, idiot. Z minus z naught times what? Times h of z, such that h of z naught is not equal to 0 again. So what happens when I look at f of z over g of z? F of z over g of z, what's that look like? Looks like we've got, z minus z naught times h of z, right? Divided into a0 plus a1 z minus z naught, a2 z minus z naught squared. And how does that simplify? So I can rewrite that a little bit. That gives me a0 over z minus z naught times h of z plus a1 over h of z plus a2. I'm not sure this is actually helpful. I mean, that's not a Laurent series, right? I've got this big old annoying h of z in my denominator there. Prove rule 3 using rule 1.
So say, what's the limit as you approach z naught of z minus z naught times f z over?
Ooh, I like it. So what are we supposed to do? If rule 1 is successful, we should be able to calculate the limit. We should look at the limit as z goes to z naught of what? Does it make sense to do that?
I know that we can write, well, you already wrote g.
Oh, okay, so, well, I don't know. I don't know about f. I don't know that f doesn't have. The thing is, the ratio of f with g, I'm not sure that that's just a simple pull.
Because you don't know if f is not 0.
Right.
I think that was in the notes. That
Oh, have I forgotten my rule 3?
I think the notes proves two cases. It has one where f at z naught is 0. So there's one where f at z naught is 0, but it's a 0 order 2 or higher.
Tell you what, I will come back and start next class with the proof of this rather than butchering it at the moment, right? Let's actually go on and use these rules to, anyway, I think everyone agrees that 4 we can prove from 3. And I think everyone agrees that I should put rule 2 on the final. No? No. Just kidding. Let's actually apply these to calculate something else actually instead. But yeah, but glancing at the notes, it's going to take me 10 minutes. So I had foolishly hoped that I could just beast my way through it, and not always successful. But I do know that we could calculate at least a couple more examples here. So, for example, let's look at the residue of 1 over z squared plus 1 at I, right? So, of course, this is nothing more than z plus I times z minus I, right? So the fact that these are equal reveals immediately that that's a what? It's got a simple pole at I, right? I mean, you can see that that is a simple pole. And so we can use rule 4. And what's rule 4 say? It says it's 1 over the derivative with respect to z of z squared plus 1 evaluated at z equals to I, which is 1 over 2I. And likewise, the residue at the minus I is 1 over 2z evaluated at z equals to minus I, right? Which is minus 1 over 2I. This is actually pretty neat because it means that you can calculate partial fractions without calculating partial fractions, right? Because you know that 1 over z squared plus 1 looks something like a over z plus I plus b over z minus I, and those a and b must be 1 over 2I and minus 1 over 2I.
So the d over dz you put in there, is that like an equivalent formulation of rule 1?
Yeah, it's the derivative of the denominator. Rule 4, actually.
Oh, rule 4.
Rule 4. I'm using rule 4 at the moment. Let's see here. Now this one's, so this right here, I tell you what, look at this one. The residue of e to the z over sine z at pi. All right. Imagine yourself without rule 4 or rule 3. We need rule 3 for this one, right? I think. So you find the series expanded about pi for the exponential and for sine. I mean, we can do both of those things. And we can even divide the series and start calculating Laurent series term by term, right? But this rule 3 is so much simpler, right? Because all you got to do is go, okay, so it's e to the pi divided by cosine of pi, because this has a simple pole at pi, right? Sine has a simple pole at pi. So by rule 4, sorry, simple 0. Eventually I'll get it. Hey, but I got some good company with you guys. So, oh, I'm sorry, is that too soon? But rule 3. Many of you will be dropping this second test, I will tell you that. I'm quite certain that most of you will do better on the final. But anyway, there you go. Not so much as a Laurent series in anywhere to be seen, and there's the residue. So through judicious use of rules 1, 2, and 3, and 4, we can calculate residues very, very nicely. Yeah. You might say bigly. Oh, I'm sorry. I seem to have gone over time. I shall shut up. Let me get you your test back.